So today we're just going to look at graphing the basic trig functions, but now using radians rather than degrees. So we'll start with our sine curve, and we know that it goes between -1 and 1, so I'll mark that on the y-axis. And on the x-axis I'll mark off every, 90 degrees, but I'm using radians, and I'm also being a bit lazy and not labelling every second one, so I'm just going multiples of pi, I'm labelling. So if I was to draw a sine curve, I always start by saying what's happening at the origin. And so at 0, we know the sine is 0, so in fact we are at the origin. And then we know that sine of 90, or pi on 2 if we're talking about radians, is 1, so I plot that one in, and then I know it zigzags all the way along. So down and up and down and up, and then to the left, down and up and down, but of course it's not a zigzag, it's not a straight line, we draw a nice smooth curve. So there's our basic curve y equals sine x. What can we tell from this graph? Well, the domain's all real x, there's no breaks in the graph at all. The range though, it's only going in between -1 and 1. It's an odd function, so I can see the rotational symmetry. So therefore, I know that the sine of negative x must equal the negative sine of x, so that could come in handy when we're playing with trig identities and things like that. When we're talking about trig curves, we have an expression called period. And a period is just how long it takes until the curve starts repeating. And it has to be going in the same direction. So you might look at it and say, oh, hang on, it only takes pi. So we can see at pi it's 0, at 2 pi it's also 0, so it looks like the period's just pi, it only takes pi to get back. But it's got to be going in the same direction. At pi it's going down, at 2 pi it's going up. It's not until we get to 3 pi it's going back down again. So we could pick any point on the curve. So for a sine curve, it takes 2 pi radians until it repeats. And the amplitude is how far up and down it goes from the axis of the actual curve itself. And so the amplitude is 1 for a basic sine curve. All right, let's have a look at cosine. Again, it also goes between -1 and 1. And once again, I'll mark off every 90 degrees or pi on 2 radians. So at 0, well, we know the cosine of 0 is 1. So this time it'll start up at 1. And then at 90 degrees, or pi on 2, it goes down to 0. And again, we get that zigzagging, so down and up and down and up. And again, we get a nice smooth curve. And basically, it's the same curve, if you think about it. It's just that I've shifted it. So we'll see the same sort of things. The domain is all real x. The range is in between -1 and 1. But in this case, it's an even function. It's got reflectional symmetry. So we know then that the cosine of negative x would be equal to the cosine of x. Its period's also 2 pi, its amplitude is 1, and as I was saying, really, all we've done is we've drawn the sine curve, but we've shifted it. So we have actually drawn, well, first of all, we got the sine curve. Negative x would mean reflect in the y-axis. So if I'd reflected it in the y-axis, and then shifted a pi on 2 units to the right, I would get the cosine curve. And that's because they're complementary ratios. All right, let's try tangent. Okay, I haven't bothered marking off on the y-axis because a tan curve doesn't have an amplitude. It goes all the way up to infinity and down to -infinity. But once again, I'll mark off every pi on 2. So what happens at 0? Well, tan of 0 is 0. But then, at pi on 2, it's undefined. So I'll draw in a vertical asymptote. And that pattern repeats. So 0, asymptote, and back the other way as well. Now there I've just drawn in the section between pi on 2 and minus pi on 2. When you are drawing the tan curves, things to remember. It's not a cubic, so you don't come in and draw it flat like the cubic. It should be going through the origin at 45 degrees. When you draw it. But that pattern repeats in between every asymptote. So the domain, well, it's all real x, except we've got these breaks, first of all at 90 degrees, or pi on 2, but then every pi before and after that. So I can say plus pi k, where k is a whole number. The range is all real wide, there's no breaks there. It has rotational symmetry again. So we know it's an odd function. So therefore the tan of minus x is minus tan x. The period for this one though is only pi. Takes every pi for it to repeat. And there's no point talking about the amplitude of a tan curve because it doesn't have one. Let's have a look at one of the reciprocal graphs. So cosecant. The way I'm going to draw it is by drawing the reciprocal of the sine graph. Okay, so we know that cosec is 1 over sine x. So if I draw in the basic curve y equals sine x, and then we're going to take its reciprocal. So what did we say that? We said, well, the x-intercepts would become asymptotes. So I've drawn those in. Well, we know that when we turn 1 upside down, we get 1. So all of those peaks and troughs, they will stay at those points. And we said, whenever the curve's less than 1, it'll become greater than 1. And so we get that graph. Because the original graph, the sine curve, was never greater than 1. So I knew graph can never go less than 1. I've got to bend towards the asymptotes. Other things we call where the original curve was concave down, the new curve is concave up, and things like that. So we get these series of U shapes for cosec x. Sec x would be a similar one, but shifted along. And cotan is also similar to the tan curve with a bit of a shift. I won't draw all of them up. I'll just stop it there. So 11J, 2 to 15, is just looking at those basic trig curves and questions on that.